Okay, and I would start webinar on digital twin technology and application for the refrigeration system, or the cooling and refrigeration system, and how is technology allow us to save electricity, so it saves CO2 emissions also, but today it's very important just due to electricity price save our money. Today we will talk about energy advice, who we are, what and how we are, what problem and how we are solving this optimization problem, what results we achieved and what is experience, what is the technology inside digitalization process by itself, and what is return on investment on such type of investments. About energy advice, we're a technology company in the market for last 10 years. Part of a business is auditing, technological energy efficiency. Another part of the business is IT solution, as SaaS, energy advice software as a service. It's cloud-based solution for digital twins. In our portfolio, quite many digital twins. You could participate in our seminars, webinars on digital twins, and today we are talking about a SaaS cooling solution as the same as SaaS platform, a cooling digital twin. And our mission is to reach your CO2 targets. And what problem we are solving? In fact, we are solving the main problem of how to save expenses on the cooling without the hardware change. We know that changing from one compressor to another, adding economizers, changing condensers, and many other hardware changes could make effect and save our electricity and cost for electricity, but this is quite big changes, and probably we have another potential how to reduce electricity consumption for the same amount of energy and for the same technological requirements, I mean for the same cooling temperature. And we introduced it as a cooling digital twin, which is in fact allow to reduce electricity consumption without investment to the hardware. And how we are solving this problem? First, of course, we collect data from your SCADA, from your PLCs. If you have SCADA, usually in the SCADA you will have OPC server, and if you have PLCs, we make direct data collection from PLCs, adding to your premises only one thing. It is data collection software, which connect to PLC or OPC. And collect data in real time and send to the cloud. Digital twin inside the cloud, later we will discuss about. And we have advanced process control. I mean, from the cloud, we send back commands, optimization commands to PLCs, to your cooling or refrigeration system, in order to reach goal to increase efficiency and reduce electricity consumption. So this is maximum what we must to do. We should connect to your system, collect SCADA and PLC, or PLC if it's a smaller system, PLC's data, because inside the SCADA and PLC, inside the controllers, we have all data what we are required to have a digital twin solution. In what kind of systems our solution is applicable? In fact, we have reference for the CO2, ammonia, Freon system. We have experience on multi-stage, single and multi-stage system. We have experience for the chilled water and glycol when the machine is working and producing cold chilled water. In fact, many type of vendors, so we can tell that we are vendor independent, and it's applicable for industrial and commercial refrigeration. Today, we more or less focus on industrial and commercial because it is highest capacity, cooling capacity, highest installed electrical capacity, and it is you have highest expenses, and it could give you very good ROI in very short term. What results we deliver? In fact, reduce electricity consumption through advanced process control. Of course, we do inventory of your equipment, IT infrastructure, your PID regulators, what are inside. So we digital twin catch everything, all problems what you have. Sometimes you may do not know of these problems. Of course, it's increased digitalization maturity, and we monitor also not only consumer side how the cooling energy is consumed, but also condensers, economizers, compressors, evaporators efficiencies. It's also important because deterioration of efficiencies would lead to decreased efficiency overall of a system. It's increased electricity consumption. Couple slides on the experience and examples. What we agreed with the clients. Rokiškio cheese Sūris is a cheese producing company, dairy company, and we saved 20% energy. We approached it to us with a question: can we optimize or reduce electricity consumption for the chilled water production? We have two loops. One is chilled water, another is -20 for the storage. And we achieved 20% meat processing plant, Krekenava. We wondered it also 37% of electricity reduction. Why we wondered? Because we expected 10-15%, but due to very high dynamic in production, dynamic in amount of product we produce, and during the same day, we reached quite big potential. We have ammonia system -40 and -10. Previous example, Rokiškio, we have ammonia system. Of course, we have many other signs where we already installed a SAS cooling system. And what is inside the technology? To tell what is inside in the technology, first we should understand the issues what the manufacturers, in fact, face during the manufacturing process of a system. In fact, it's not impossible to account or meter cooling energy what was produced, especially in ammonia, CO2, and freon system, where is direct fluid is ammonia and CO2 and then freon, because we cannot install energy meter. In water, in chilled water side, yes, we can install energy meter and account what was the cooling energy produced. But in ammonia, freon, and then CO2, when the agent is act directly to a refrigeration process, we cannot install metering because we have two-phase flow. Supply is one-phase fluid, and return is two-phase inside vapors. So we cannot account. So we never know what is the real scope of the system. And of course, about the KPIs, of course, it's hard to define these KPIs. Usually, we have electricity ratio with product. And this KPI usually varies over time, and we never know the reasons. We can consider later we can consider what was the reasons of these fluctuating KPIs, but we probably were affected by outside temperatures, infiltration to the building, freezing of the freezers, amount of products, and etc. etc. So many things which affect on KPI. And as we describe hidden potential, we should know always, especially when we are looking to reach CO2 neutrality, we should know what is the hidden potential. What does it mean, hidden potential? We need to calculate ratio, what is energy required theoretically for cooling, chilling, or freezing, divide by real electricity consumption for that process. One, it is theoretically you consume energy as, and better it's impossible. It means one ratio, and less ratio show you potential, how far you are from your with technology, from where you could be with technology. And this, of course, digital twin online can describe where you are. So what market propose? Market propose probably two technologies, and our technology would be third type of a technology. One technology is just to put some PLCs, controllers, to consumer side for the cold room, for example, and monitor what is the overcooling, undercooling of your room, and probably, of course, save some not to deliver cold or thermal energy to the room. And another type of technology is like monitoring. I just monitor something and maybe we would see something. But probably these technologies don't save you electricity, or it's safe in very, very long period, and you probably never know what are real results. And what we acknowledge that so we need to save electricity, and how to do this. Of course, I would ask a question, and probably you can write to the chat. One of an answer is increase COP, coefficient of performance. Coefficient of performance, you know well, it's the ratio of thermal energy divided by electricity, or electrical efficiency ratio or factor. What's next? What would we can do? We can reduce transportation losses. Yes, we have pipes from the refrigeration system to consumer. We have pipes, and then better insulation, lower losses probably. What parameters could make effect on? So hardware change that we discussed it, and probably best solution is to change, increase evaporation pressure or temperature. Why? Because it reduces compression ratio. And if we reduce compression ratio, that means a compressor would operate in better efficiency. Compressor by itself, better efficiency. So hardware change to costly solutions. So we should somehow manipulate evaporation pressure in order to have better compression ratio. And what we delivered for that systems like ammonia, like CO2, like freon, where the agent directly acts in the process, cooling process. We made digital twin full model of compressor, evaporation site, and then full compressor station, including consumer sites, and using only data what we deliver, what the PLC or SCADA OPC delivered to us. and we capable to calculate what is the cooling energy consumption now at that moment. And if we know the cooling energy consumption now at that moment, we are capable to adding electricity metered value. We can calculate very well coefficient of performance. But if we know what is the demand now at that moment, we can easily adopt temperature, evaporation temperature and pressure according to demand. So it's like demand response, or in other words, we respond, or chiller or freezing system is responding to the demand. So in the picture you can see, we started with a project with -10 degree. It was defined by manufacturer when the system was installed, but we need -10 degree for the freezing process. It's ammonia, probably in this example was. And during its red line, during the operation, when we installed digital twin, we found that demand is fluctuating quite much, and we need to optimize evaporation pressure and temperature, and we started to change evaporation temperature according to the demand. And it's a very short period on January to February. You can see how it's fluctuate. It's fluctuate quite a lot. This evaporation temperature, but this fluctuation is required. Why? Because in some particular moments, evaporation temperature was required quite high. Pressure quite low or temperature quite low, because demand was high, and our system as cooling was increasing or reducing temperature, or increasing cold production, or it's reducing evaporation pressure and temperature. And in another moments, when the demand is low, the system started to increase pressure and temperature. Of course, during the summer, system would come to the mode where evaporation temperature may need at -9 and -10 as manufactured or in design stage was designed. But you see that many hours from the design maximum, we could operate in quite low levels sorry, it's higher levels of temperatures in the operation section. It's an opposite. So existing control strategy, when we do digitalization, it don't mean that we come to the refrigeration system which don't have control at all. No, that means that these systems have inside automation, and quite good automation. We have examples with well-known brands and the system like it's business as usual in all countries. But existing control strategies define to keep evaporation temperature which cover 100% situation. So we define -10 degree, for example, or -40 degree evaporation temperature to match 100% situation. And usually this is surplus evaporation temperature. Of course, it's not so good coefficient of performance, and it's higher electricity consumption. So our control strategy is to control according to demand. So higher demand requires lower operation pressure, which leads to lower COP/ER coefficient, and lower demand requires higher operation pressure, which leads to higher COP of a compressor station. So what we deliver with a digital twin together with ESS cooling? First, we monitor condensers performance. and of course make effect on condensing pressure optimization also, operation side and operators efficiencies, cooling energy balance in real time, cooling consumption forecast and comparison with real consumption, compressor station KPI, and we define also and calculate compressors efficiency by itself, so we can check whatever compressor by itself only as a device as alone, is it working at good efficiency point. Equipment maintenance planning, of course, automated operation according to the electricity price is very important today when the prices are going up and down, to schedule your cooling production according to electricity price. And sometimes we can overcool, sometimes we can undercool according to electricity price. And absolutely another task, advanced process control for the just cooling energy optimization. So two approaches inside. One is to optimize production according to electricity price, so it's optimized cost, total cost. And another is optimize operation by itself. It's not including costs of electricity price. Case study, dairy company asking us, its system consists of 4 compressor, condenser, receivers, chilled water, cold rooms -2, you can see inside, and 2 compressors working in the loop. So it's 2-stage system. It's slightly different designs as usual. And we install it, digital twin, real-time data collection, implement a digital twin, calculated POP. We calculate also ammonia mass flow, and deliver digital twin calculated each 5 minutes. Another case, the company was looking also to reduce electricity consumption, and what we found that the evaporator is working on -40 degrees. But because we calculate energy demand, what is the cooling energy demand, what is consumption, we found that during the night shift they drastically reduce, and we don't need absolutely we don't need such -40 temperatures. So yellow, it's control set points. You can see it's also slightly varied during the night according to the need, but variation is lower, and during the day we work at quite fixed. But it allows us to from -40 to -40. Of course, it's February. During the summer, it's reached -40 also, but it allows us to go to -37 and night shift -31. So for this -40 coil, we reach at near to 30% of energy savings from -40 coil. The same graphic I described it earlier, and the results, what we reached, it was 20% of energy reduction, because we started from -10. We found that -10 is good solution only for the summer period, coldest time, and system adopting evaporation pressure according to the demand, and it allows us to save near to 20%, assuming 5% energy savings per 1 degree of evaporation temperature rule. Another type of a system, it's commercial side. It's not industrial, it's commercial side. The system company also was looking how to optimize electricity, how to reduce electricity consumption for the chilling cooling process, and style of compressor station is two chillers. One chiller inside consists of two compressors. Another chiller consists of two compressors. It's prepare cold water, maybe glycol, I don't remember now, and is delivered to the load. And also it was +8 production. We acknowledge that it could work between +8 and +12, and savings at 20%. So perfect match. How to understand fast does our system is suitable for you, for your application is, of course, does your SCADA have OPC if it's industrial application? Does your cooling energy consumers have temperature sensors, or and these sensors are connected to OPC, to SCADA? Do you have this data? PLC control logic allow change some parameters, such parameters like evaporation, condensing pressures or temperatures. Can we change compressor capacity? And can we change variable frequency drive compressor side frequency? If yes, so we can install. Also, it's one trick, it's not written in the slides, but what we found that optimization of compressor capacity control strategy in some cases allow clients not to buy a variable frequency drive. Multi-stage or single-stage and electricity meters should be installed on the compressors. To meter electricity compressors of compressors, and if you have variable frequency drive inside have frequency metering value and electricity active power value, so we don't need install electricity meter. Three examples of quite different, for example, two compressors on one stage, and other two compressors working on another stage, and condensers, and we deliver cold chilled water and minus water, -2, or ammonia or CO2. Another example is three compressors working in minus, it's CO2, I remember this example. Working in three compressors working in -40, four compressors working in -10, chilled water, economizer installed, and then a condenser, and as showed earlier, Rokiškio cheese producer with four compressors on chilled water and two compressors -20. If you have commercial application, so usually it would be like some PLCs, and what we need communication for the data transfer, data communications like Modbus, Profibus, Profinet, BACnet, or some kind of protocols. Cooling energy consumers should have temperature sensors, and this temperature should be connected to OPC, PLC, or whatever. Some PLC logic controller should allow us make access and control of evaporation, condenser side, compressor capacity, variable frequency drive frequency. Of course, electricity meter, you may ask us to prove that our system is working, so you need electricity meter installed. And if variable frequency drive installed, since it has inside active power metering, and you don't need to install extra electricity meter. And some applications where one chiller, one compressor working in water loop, It is one chiller with two compressors, or two chillers with four compressors inside, working to the loop and how the digitalization process happening. If we would go to agreement to install, of course, we would collect data, what's happening inside, connect this data to data collection software, and everything would be on the cloud. We analyze, run digital twin, and you become a user. You have advanced process control, optimized process control. Usually your IT guys would ask about IT security, automation security, and we work according to IEC standard for industrial communication networks and network and security, system security, and part 3, system security requirements and security levels. If you would have later question, I can make more comments, but your industrial application is divided to the layers. Layer 0 and 1 is related to your controllers, hardware. Level 2 is related to servers and workstations. Level 3 and 5 is 3.5 is related to BMS, like power plant, process historian, the data collections, FTP servers, etc. Level 4, or sometimes divided to 4.5, is like office applications, VPNs, proxies, integration buses, emails, and level 5 is somewhere on the cloud. And what we do, we install OPC. You have OPC. We in your workstation level, SCADA level, and we install data collection, energy device data collection software, and which is capable working only to one way to read data from OPC, or in some cases it could be controller. So it's read data. Of course, this connection is firewall. This is firewall sign. And from a data collection software and proxy server, we deliver data to the cloud. When we write commands back from the cloud, optimization commands, we write back through different absolutely path. It's another route, another channel. And we deliver commands each minute to proxy, to data writer software, and writer software put the data to the OPC box. And with OPC, of course, send commands to PLC. Return on investment, we believe that return on investments on IT automatization should be less than 1 year. So if it is higher than 1 year, that means that something is in a bad way. So we should consider how to optimize investments also. So what we reach, okay, some marketing numbers, but technically in refrigeration, what we can reach 10%, in fact, we can guarantee. Reduction of electricity, and sometimes happen 15, 20, sometimes 25, even 30%, but it depends on the fluctuation of your production side, how often and how is changing your production side. And if it's changing over a time during seasons, during hours, yes, you have potential 15-20%. And of course, we are not alone, working with many types of digital twins in industrial applications, and a couple of brand signs on the table. So I have finished it. I have a couple questions about how long does it take to run digital twin? Usually it's 1 month to data collection, and then 2-3 months to run digital twin by itself, and then close deal for us. What is the difference between monitoring and digital twin? Digital twin inside have mathematics which process monitored value and make energy, mass and energy balance online. It's very critical. And of course, we add extra on that. It's not like a digital twin with just we calculated some KPIs, but we make advanced process control in order to reach these electricity reduction targets.